Hello everybody, my name is Jake Sekosky,
I'm Martin Heraldez.
and this is our lab report on the Michelson Interferometer. This is lab 7 of OPTI380. So the main objective for this lab is to calibrate a Michelson interferometer by using a helium neon laser. We essentially count the number of fringes, plug it into an equation, find a calibration factor, and we're able to use this to find the wavelengths of different sources. We'll also be able to find a wavelength separation of a doublet by observing the nulls in between fringes and making a calculation based off of that.
So our goal in part A was to create a calibration factor that allows us to relate the micrometer take readings to the optical path-like difference between the two mirrors, which would allow us to calculate the wavelengths in part B. We did this by aligning the system to create a fringe pattern and then rotating the micrometer in a clockwise direction and counting how many ticks it took to cover 100 cycles of fringes through the center. So in part B, we sought to actually apply the calibration factor from part A to find the wavelengths of a mercury lamp and a sodium lamp. And to do this, we adjusted our setup by removing the lens that was present in front of the laser before and removing it completely for the mercury setup and adding a diffuser for the sodium setup. And we only used 50 ticks as opposed to 100 ticks as in part A. Our goal in part C was to find the wavelength difference between the two emissions from sodium. And to do this, we just found the distance between nulls, which is essentially when the fringes went blurry, and divided the average of the two wavelengths by this distance to get the wavelength separation.
For part A, we counted N to be 32, which when plugging in the wavelength of a helium neon laser gave us a calibration factor that we could use in part B. This was essentially done by swapping the calibration factor and the wavelength in the respective parts of the equation in order to find the wavelength. We were able to get very accurate values, with the highest amount of error being 1.39% and the lowest being 0 error, as we expect with the helium neon laser.
So for part C, our expected value of 0.597 falls pretty close to our actual value of 0.599 nanometers, which is likely due to the fact that we had to reverse engineer the ticks for this, since we used a different tick reading on the micrometer, and we found it to be about 10 micrometers per tick, which results in a 20 micrometer optical path-like difference.
So in conclusion, we found a calibration factor in part A that allowed us to calculate wavelengths in part B of various sources. The only problem with this is that you had to be very precise when counting the different fringes, otherwise the number would be way off. In addition, by finding the distance between two null fringe patterns, we were able to find the wavelength separation of a doublet to a very accurate degree.